Jai Hind students, welcome to my YouTube channel. Students, always dream big, think big. You may not be perfect in many things, it is but obvious. One can't be perfect, isn't it? So you may not be perfect in many things, it's understandable. But many things cannot be perfect without you. I repeat students, there are many things which cannot be perfect without you. It means that every one of you is special in your own little ways. So, give due importance to yourself, love yourself, appreciate yourself. Right? So, with that students, let's begin today's session. In the previous 2-3 lectures, we have discussed diamagnetism on the basis of electron theory. Then we have discussed paramagnetism on the basis of atomic theory. And we have discussed ferromagnetism on the basis of domain theory. Now, in this particular lecture, what we are going to do is, we are going to bring out the essential points of difference between diamagnetic substances, paramagnetic substances and ferromagnetic substances. Right? So, let's start this topic. So, we will be bringing out the basic essential difference between these 3 types of magnetic materials. And these are the points through which we will differentiate these 3 magnetic quantities, right? So, these are the points of difference. So, let's consider the first one, paired or unpaired electrons. Now, we all are aware, students, we have done it in detail. Every atom of a diamagnetic substance possesses paired electron, isn't it? So, diamagnetic substance, every atom, it possesses paired electron. Okay. Paramagnetic, it possesses unpaired electron, right? Para and ferro both possess unpaired electron. So in this case, both para as well as ferromagnetic substance possess unpaired electron. This is one of the basic difference between dia-para or dia and ferro. Diamagnetic substance possesses paired electrons. So we are aware in a pair, it can be assumed as if the 2 electrons of a pair, right, forming a pair, they are having orbital motion around the nucleus in the same orbit but in the opposite direction. If one is assumed to be moving in the clockwise, then the other one will be assumed to be moving in the anti-clockwise direction. So what happens is, due to the orbital electrons, due to the electrons moving around the nucleus in certain circular path, certain magnetic moment is associated with it. Now, due to the presence of paired electrons, these magnetic moments of the 2 electrons forming a pair are equal in magnitude and oppositely directed. So, net magnetic moment of an atom that possesses paired electron is always 0, right? So, magnetic moment of each individual atom, net magnetic moment over here is 0. Clear, students? The paramagnetic atom possesses 0 magnetic moment due to the fact that it possesses paired electrons. So, the magnetic moments being equal in magnitude and opposite directed get cancelled out, they get nullified. While on the other hand, for para and ferro, each atom of a paramagnetic substance or ferromagnetic substance possesses unpaired electron. So, due to the orbital motion of an electron around the nucleus, it possesses some magnetic moment which remain uncancelled due to the unpaired electron. So, every atom behaves as an atomic dipole because of the fact that it possesses some non-zero finite value of magnetic moment, right? So, every atom or each atom possesses magnetic moment. It possesses magnetic moment. So, every atom of a paramagnetic or ferromagnetic substance behave as an atomic dipole. So, same is the case with ferro as well. Every ferromagnetic atom possesses some non-zero finite value of magnetic moment. towards a magnet. Now when a diamagnetic substance is brought near a magnet, then it is found that it is weakly repelled by a magnet. Weakly or feebly repelled by a magnet. It is because of the fact that a diamagnetic substance get feebly magnetized in a direction opposite to that of the magnetizing field, isn't it? So, diamagnetic substance, it get feebly means weakly repelled by a magnet. While on the other hand, students, we have discussed paramagnetism on the basis of atomic theory, and there we have discussed a paramagnetic specimen under the influence of magnetic field. It get feebly, weakly magnetized along the direction of the external field. So, a paramagnetic specimen, it get feebly or weakly attracted by a magnet. Right? While in the case of ferromagnetism, students, we are aware, there due to the exchange interaction, an unpaired electron of an atom strongly interacts with unpaired electron of neighboring atom. So that the atoms, they tend to align themselves in a common direction in a certain small volumes which are known as domains. So instead of considering individual atom in ferromagnetic substances, we consider a group of atoms having common alignment. Those are known as domains. Interactions are stronger. So in this case, a ferromagnetic substance, it get strongly attracted. It get strongly attracted by a magnet. Right? Okay. Next point of difference is alignment when the dia, para or ferromagnetic specimen is suspended under the influence of uniform magnetic field, right? Suppose these are the two poles. This is the north pole and this is the south pole. It provides a region of magnetic field directed from north to south. And let us consider a diamagnetic specimen is freely suspended. So it is found that under the influence of this external field, it is found that this diamagnetic specimen, it tend to align itself perpendicular to the direction of the magnetic field. I will show you with the help of this particular diagram. Suppose this is a diamagnetic specimen. So when suspended freely, it tends to align itself perpendicular to the direction of the magnetic field. Like this. So this is the direction of the magnetic field. And it aligns itself perpendicular to the direction of the magnetic field. So whenever a diamagnetic specimen is suspended freely, then the diamagnetic specimen tends to align itself perpendicular to the direction of the magnetic field. That is what it is observed, right? Because of the fact that it gets feebly magnetized in a direction opposite to that of the external field, isn't it? So it gets feebly repelled by a magnet. Anyway, for paramagnetic substance, it is observed that the paramagnetic substance, when suspended freely, it slowly and steadily aligns itself along the direction of the magnetic field. So the diagram in this case for the paramagnetic specimen would be somewhat like this. Like this. So it will tend to align itself. So this is the direction of the magnetic field. So for a paramagnetic specimen, when it is suspended under the influence of external field, it slowly aligns itself along the direction of the magnetic field, right? And for ferro, the same thing, but here it gets slowly aligned itself, but here it readily aligns itself. So here it is the case of slow alignment. It is the case of slow alignment along the direction of the magnetic field, Here it is the case of readily aligned along the direction of the field, along the direction of external magnetic field. So diagram would be same. So when a ferromagnetic specimen is suspended freely under the influence of some external magnetic field, then it readily aligns itself. It readily aligns itself along the direction of the magnetic field. So this is the direction of the magnetic field. It will readily align itself along the direction of the magnetic field. Right? So this was the difference between dia, para, ferro in respect with the alignment when a freely suspended magnetic specimen is under the influence of external magnetic field. Now students, let's proceed to the fifth point of difference, which is the movement of a magnetic substance in the case of a non-uniform magnetic field. Non-uniform magnetic field means in some region the magnetic field, its strength will be stronger, while in some other region the magnetic field will be weaker. It's not constant, right? Strength varies from place to place. So that's a non-uniform magnetic field. So it is found that when a diamagnetic specimen is placed in a non-uniform magnetic field, then it tends to move from the stronger part of the magnetic field to the weaker region of the magnetic field. Stronger to weaker, right? So it can be experimentally verified. Suppose students, this is a U-tube, and let us consider these are the two poles of a magnet. This is north pole and this is south pole. In the absence of magnetic field, the level of the specimen in both the limbs of the U-tube must be same, isn't it? Both the limbs are of same cross-sectional area and same radius. So here, it is observed that in this case, the limb where the poles of the magnet are placed, here the diamagnetic specimen get depressed. Obviously, in the other limb, the level will get raised. So it clearly indicates that a diamagnetic substance, when placed under the influence of non-uniform magnetic field, this is the place of this is the place of magnetic field where here the magnetic field is almost zero, right? So it tends to move from stronger region of the magnetic field to the weaker region. So in a non-uniform magnetic field, diamagnetic substance tends to move from the stronger region of magnetic field to the weaker region of magnetic field. So it moves from diamagnetic substance. It tends to move from stronger magnetic field, stronger region of stronger magnetic field, to weaker magnetic field. Okay. Let's discuss the case of paramagnetic. The paramagnetic behavior is exactly opposite. So here dia, it tends to move from stronger to weaker. In the case of para, it is found that when it is placed under the influence of non-uniform magnetic field, it tends to move from the weaker magnetic field to the region of stronger magnetic field. So, in this case, it is observed like this. Suppose these are the poles, right? So here the magnetic field is stronger, here the magnetic field is almost absent or negligible. So here it is found that in this case, the level of the paramagnetic material will increase in this level, while in this case it will get depressed. So it indicates that the paramagnetic material, when placed under the influence of non-uniform magnetic field, it tends to move from the region of weaker magnetic field to the region of stronger magnetic field. So a paramagnetic substance, it moves from region of weaker magnetic field to region of strong magnetic field. Right? For ferro students, ferromagnetic substance substances are not present in liquid or gaseous form. It can be present in powdered form, solid or powdered form. So basically, it is observed that when ferromagnetic substance in the powdered form is kept on a watch glass and is placed on the two poles of a magnet. In the first case, the poles are very close to each other. So the region between these two poles is of strong magnetic field, while the region, in the extreme region, the magnetic field is quite weaker. In case the poles are separated from each other, then this region, extreme region, will have strong magnetic field, while the middle region will have weaker magnetic field. Now look, when ferromagnetic substance is placed on the watch glass and it is in the powdered form, then in this case what happens is, it is like this. An elevation is formed at the middle, like this. So the ferromagnetic material tends to travel from the extreme region to the middle region, indicating that it travels or it moves from the weaker magnetic field to the region of strong magnetic field. I repeat students, here in the extreme regions the magnetic field is weaker, while in the middle portion the magnetic field is stronger. So a heap is formed near the middle of the watch glass, indicating that the ferromagnetic substance tends to move from the region of weaker magnetic field to the region of strong magnetic field. So its behavior is same as that of the paramagnetic substances, right? While on the other hand, when the pole pieces are separated or there's a huge gap between these two, then in the middle region the magnetic field will get weaker, while in the extreme region the magnetic field will be stronger, comparatively stronger. So here, if the ferromagnetic substance is placed on the watch glass in the powdered form, then a depression will appear in the middle, like this. It will be like this. So there will be a depression in the middle. It means that the ferromagnetic specimen in the powdered form tends to move from the weaker region of the magnetic field to the stronger region. Again, it explains the same observation, right? So from this experiment, it can be safely concluded that both para as well as ferromagnetic substances, when placed in a non-uniform magnetic field, tends to move from the region of weaker magnetic field to the region of strong magnetic field, right? Okay, let's concentrate on the sixth point of difference, which is the temperature dependency. Now, as we have discussed, diamagnetism is independent of temperature. So, diamagnetic substances, it is independent of temperature. That is, diamagnetism or diamagnetic behavior is independent of temperature. While on the other hand, students, we have discussed in detail, paramagnetic substances, it obey Curie's law. So obviously it is temperature dependent. It obeys Curie's law, which states that the magnetic susceptibility of a paramagnetic substance is inversely proportional to the temperature of the specimen in the absolute scale, right? So with the increase in the temperature, the paramagnetic substance will tend to lose its magnetism, right? Ferromagnetic substance, it also depends upon temperature, but it do not obey Curie law. Instead, it obeys Curie-Weiss law. So it is also temperature dependent, but it obeys Curie-Weiss law, which states that the magnetic susceptibility of a ferromagnetic substance is inversely proportional to the temperature above its critical temperature. T minus Tc is the temperature above its critical temperature. Tc is the critical temperature in the absolute scale. It is that temperature beyond which a ferromagnetic substance starts behaving as a paramagnetic substance, right? Okay, now let's discuss the next point of difference, which is the density of the magnetic field lines inside the material. Now suppose students, a magnetic specimen is placed under the influence of uniform magnetic field. So this is North Pole, this is South Pole, and it will act as a source of uniform magnetic field. This is the region where, in the absence of any magnetic specimen, the magnetic field can be considered to be uniform. So it may be represented by equidistant parallel lines, right? Now what will happen when a diamagnetic specimen is placed under the influence of this uniform magnetic field? Then, as we have discussed, diamagnetism on the basis of electron theory, that it gets feebly magnetized in a direction opposite to that of the external field. So external field is directed along this direction from north to south. So it will get magnetized in an opposite direction. It will get magnetized in this direction. So this will be the direction of its magnetization. Clear, students? So first point to be noted is that a diamagnetic substance get feebly magnetized in a direction opposite to that of the external field. Now direction of external field will be from north to south, isn't it? Now in this case, regarding the density of the field lines inside the material, the diagram would be somewhat like this. Actually, the external field lines will get repelled from this diamagnetic material. It will be somewhat like this. So what this diagram suggests is the density of the field lines inside the material will become slightly less. So basically, this diamagnetic specimen repels the magnetic field lines. Its conducting power to the passage of magnetic field lines is not so good. It actually is repelling the external field lines to pass through it. It is not allowing it, right? So it is getting repelled. The field lines are getting repelled from it. So as a result, here the density of the field lines inside the material slightly decreases. So density of the material slightly decreases. The density of the field lines inside the diamagnetic material slightly decreases, right? Now coming to paramagnetic substance. Paramagnetism we have discussed in detail with the help of atomic theory, and we have discussed that it gets feebly magnetized along the direction of the magnetic field. So this is the direction of the external field, so it will get magnetized in the same direction. So this will acquire north polarity, while this end of the paramagnetic specimen will acquire north polarity. This will acquire south polarity, this will acquire north polarity. So it will be like this. Magnetic moment, it's directed from south to north, and that is the direction of the intensity of magnetization also, that is from south to north, right? So in this case, the diagram would be somewhat like this. So in this case, the density of the field lines inside the material will slightly increase. The density of the field lines inside the paramagnetic material slightly increases. Clear, students? It's pretty evident. So here they are getting attracted towards the paramagnetic specimen. So the field lines are passing through the paramagnetic specimen, right? So the field lines, its density inside the material of the paramagnetic specimen slightly increases, right? And it gets magnetized along the direction of the external field. Now regarding ferromagnetic, there is no such basic difference between para and ferro. Whatever here the process takes place slightly, weakly, there it will take place readily and greatly, right? So in this case, again, a ferromagnetic substance, it gets strongly magnetized along the direction of the external magnetic field. So it will get strongly magnetized along the direction of the external magnetic field. And students, in case of a ferromagnetic substance, all the external magnetic field lines will tend to pass through the specimen of the ferromagnetic substance. So they will be drawn into the ferromagnetic material. So the diagram would be like this. So the field lines, its density will be very, very large inside the material. It will be like this. All the field lines will tend to pass through the material. All the field lines will get attracted, or the conducting power of the ferromagnetic material towards the passage of magnetic field lines is very large, right? So this is the diagram. So in this case, the field lines, its density greatly increases. Students, just with the help of the diagram, you should be able to differentiate between dia, para and ferro. So this is a very, very important diagram. This is a very, very important diagram. First and foremost, observe the polarity, isn't it? So diamagnetic substance, it gets feebly magnetized in a direction opposite to that of the external field. External field is from left to right. So it will get magnetized in a direction opposite to that. In this case, para, it will get feebly magnetized along the direction of the external field. And in this case, it will get strongly magnetized along the direction of the magnetic field. Here, the density of the field lines inside the diamagnetic material slightly decreases. Here, the density of the field lines inside the material slightly increases, right? And here, the density of the field lines inside the ferromagnetic material greatly increases, right? So, this is a very, very important diagram. Now, let's discuss intensity of magnetization. We know that, students, intensity of magnetization is the magnetic moment developed in the specimen per unit its volume, right? So in this case, it is getting feebly magnetized in a direction opposite to that of the external magnetic field. Feebly, weakly. So the magnitude of I would be very, very small and oppositely directed to that of the external field. So it will be assigned negative sign. So in this case, the intensity of magnetization of a diamagnetic substance, it has small negative value. It has small negative value. I hope you have understood this. In this case, students, paramagnetic substances, it get feebly magnetized along the direction of the external magnetic field. So again, I, its magnitude will have small value. But since it is getting magnetized along the direction of the external magnetic field, so it will have positive small value. So in this case, the intensity of magnetization of a paramagnetic specimen has small positive value. It has small positive value. Understood? What about this case then? It gets strongly magnetized, and that too along the direction of the external magnetic field. So the intensity of magnetization of a ferromagnetic material has large positive value. Right? Okay, next one is magnetic induction, which is B equals to mu naught H plus I. This is the formula, students. B is equal to mu naught H plus I. Now look, magnetic induction, as you remember, is the total number of magnetic field lines inside the material per unit area passing normally through it, right? So in this case, I has got small negative value. I has got small negative value. So obviously, B, magnetic induction for the diamagnetic substance, would be slightly less than mu naught H. Am I clear, students? I repeat, since I has small negative value for diamagnetic substance, therefore, from this we can conclude that the magnetic induction inside the diamagnetic material is slightly less than mu naught H. Mu naught H is B naught, which is the magnetic field in vacuum. So inside the diamagnetic material, the magnetic induction is slightly less than that in vacuum. That is, B is slightly less than B naught. So that is what this diagram suggests, right? Over here, I has got small positive value. Now I has got small positive value. So here obviously B would be greater than mu naught H. Mu naught H is B naught, therefore it suggests that B is greater than B naught. So the magnetic induction inside the material of the paramagnetic substance is slightly greater than that in vacuum, right? So B is slightly greater than B naught. Over here I has got large positive value. I has got large positive value. So magnetic induction inside the ferromagnetic material must be very, very large as compared to mu naught H. And since mu naught H is equal to B naught, which is the magnetic field in vacuum, therefore magnetic induction inside the ferromagnetic material is very, very large as compared to that in vacuum. I hope you have understood this topic. Okay, next is magnetic susceptibility. Now students, look, magnetic susceptibility is defined as the ratio of the intensity of magnetization to the magnetic intensity. You all are aware of it, isn't it? Actually, susceptibility is the aptness or the readiness of a magnetic specimen to get magnetized. How readily a specimen gets magnetized. Over here, I for diamagnetic has small negative value. So, chi m, magnetic susceptibility of a diamagnetic, will also have small negative value. So, chi m has, for diamagnetic material, chi m has small negative value. Right? Okay. Here, I has got small positive value. So using this formula, since I has got small positive value, so chi m will also have small positive value. So here, magnetic susceptibility of a paramagnetic substance has small positive value. While in this case, ferromagnetic substances, the intensity of magnetization has large positive value. So using this formula, since I has got large positive value, therefore chi m for ferromagnetic will also have large positive value. So chi m has large positive value. Okay, this was regarding the magnetic susceptibility. Now let's consider the relative permeability. As you are aware, it's defined as the ratio of the permeability of the substance to the permeability of free space, isn't it? So, mu r is 1 plus chi m, isn't it? And mu r is equal to mu divided by mu naught. And this is the formula. Mu r is equal to 1 plus chi m. This is the relationship between the relative permeability and the magnetic susceptibility. Now look students, chi m, it has small negative value. It has small negative value for diamagnetic substance. So, mu r for diamagnetic substance would be slightly less than 1. Is it okay, students? Just make use of this mathematical expressions, right? While in this case, chi m has got small positive value. Chi m has got small positive value. So its value would be slightly greater than 1. So mu r for para is slightly greater than 1. While on the other hand, for ferro students, chi m susceptibility has large positive value. So in this case, chi m has large positive value, so mu r will have a value which is very, very large as compared to 1. So the value of mu r for ferromagnetic substance is very large as compared to 1. Very large as compared to 1. For example, soft iron. It's a ferromagnetic substance. The value of mu r is about 800. So it's very large as compared to 1, isn't it? While the value of paramagnetic would be slightly greater than 1, 1.2, 1.3, 1.4, right? While on the other hand, for diamagnetic, the value of mu1 will be less than 1, 0.8, 0.9, 0.86, like that, right? So, knowing the value of mu1, you can easily identify whether the magnetic material under consideration is diamagnetic, paramagnetic or ferromagnetic. Clear? Okay, last but not the least, let's discuss some examples of each of these magnetic substances. Examples of diamagnetic substances. It's copper, bismuth, silver, gold, silver. These all are the examples of diamagnetic substances. Water, NaCl, they all are the examples of diamagnetic substances. While for paramagnetic students, aluminium, sodium, manganese, right? Liquid oxygen, these are the examples of paramagnetic substances. Chromium. So these are some of the examples of paramagnetic substances. For ferro students, obviously, iron, nickel, cobalt, L-nickel. So these are the examples of ferromagnetic substances. Clear? So I hope you have enjoyed this session. Actually, we have summarized every topic whichever we have studied during the last few lectures, isn't it? So these are the basic points of difference between dia, para and ferro. So in order to understand this difference between these magnetic materials in the complete sense, you need to have a proper understanding of the technical terms like magnetic intensity, susceptibility, permeability, isn't it? Magnetic induction, magnetic flux density. So these are the terms which you need to be thorough with. It is only then you can fall back to these topics and understand it completely, right? So students, that's it for this particular session. So join me in my next lecture then. Till then, bye-bye and do take very good care of yourself. Thank you.